The good news is Dell Platform Summit 2018 is launched, is announced. So the summit will be happening from 9th to 11th of August. And there will be a pre-con training days on 7th and 8th August, 5 pre-con conferences on each day. Why you should attend Dell Platform Summit 2018? Because this is one of the largest data platform conference that happens in Asia. We have 7 tracks covering all the Microsoft data stack and as well as open source technologies in the data platform world. Uh, we have best speakers traveling from all around the world. We have MVPs, MCMs, and industry experts who will be speaking at this conference. This is a 100% learning event, and this is a must attend if you're serious about data platform. The core team behind Data Platform Geeks, we have Amit Bansal, who is the founder and president. I'm Manohar Puna, I'm the vice president. Avnish Panchal is an editor, technical editor, and also a regional mentor. Prince Rastogi, who is again a regional mentor. Sandeep Pani, Yogesh Vopul, and Surbhi Agarwal, uh, all of them are part of the DPG core team who are regional mentors. And we also have the support of eDomina team, which helps us in connecting the Data Platform Day and all the work behind the summit. And Data Platform Geeks as a community, you would have already been registered on DataPlatformGeeks.com because you are attending the webinar today, and you need to be a registered member to register for the events. By joining, be part of Dell Platform Geeks because you will be notified about all the events that are being connected by Dell Platform Geeks, and also some SQLMaestros special events. You get access to all the material that is related to the webinars or Data Platform Day events that happen across India and all the online events. You'll also get access to other material like the blogs and also some conference material that is available online. You'll be part of the Asia's largest data analytics community, and you'll also be able to become a regional mentor or a speaker at one of our events. Join the largest SQL group on Facebook. It's called groups/the SQL Geeks. It is the Data Platform Geeks Facebook group and also the LinkedIn group, where you will be able to post your questions, and experts from all around the world will try and answer those questions. And over to today's webinar, I'll hand it over to our speaker, Nagaraj Venkatesan, who is a community enthusiast and also a data platform MVP from Singapore. Over to you, Nagaraj.
Thanks, Manu. Let me take the control over. Hello, everyone. Welcome to the webinar on adaptive query processing and automatic tuning. I'm Nagaraj Venkatesan from Singapore. I'm a data platform MVP and a regular speaker at data platform events in this region. Before I proceed, let me just check if everybody is able to hear me. Manu, is everybody able to hear me? Can just confirm on the chat, please. Okay. Okay, fine. I think I see a yes from most of you all. Thanks a lot once again for joining in, for tuning in for this webinar. So let me just get started. Adaptive query processing and automatic tuning. That's the topic for today. Before we get into it, I would just quickly like to know how many of you have actually seen query plans. There was a poll which Manu would have sent out. So, and just like because this session revolves around query plan, and it's good if you have some sort of background on query executions and query plans. So if not, also that's all right. Not a problem. Take you along in this session, but I'd just like to know how many people are familiar with execution plans. If you haven't voted, can you quickly vote so that okay, 43% are familiar. That's good. Okay, fine. So let's get started with this. Okay, there are just few of you. I understand from the poll that there are just few of you who haven't seen a execution plan. That's good. So let's get started. So fundamentally, yeah, what is an execution plan? Execution plan is nothing but when you submit a query, the list of things SQL Server needs to do to run the query and provide the result. List of operations it needs to do. How it works all along is the moment you submit the query, it checks for the syntax and does some processing and comes up with a execution plan. And subsequently, it is passed to SQL Server engine to run the query, run the execution plan and provide the result. But subsequently, when the same query is repeated, the same plan typically gets reused. But what's different or what's interesting about adaptive query processing is here the query. Just give me a moment. The slide. What's interesting about adaptive query processing? Just give me a moment, please. Sorry. Okay. Suddenly I was unable to move the slides, so I just wanted to say sorry about it. So what's interesting about adaptive query processing is the query optimizer is a lot more intelligent in the way in which the plans are executed. But in the older versions, in SQL Server 2016 and prior, after you have the execution plan, the SQL optimizer just follows the query engine just follows the execution plan and comes up with the result. But with adaptive query processing, it is able to adapt to what certain scenarios or certain symptoms that happen during runtime. It makes a minor adjustment to the query plan. Not just that, it also learns from previous executions. It takes feedback from previous executions of the query plan to make the minor adjustment so that the query plan is optimal. If you do not know anything about query plans, in very simple terms, query plan is just like if you go to Google Maps, if you are querying, if you are asking for the route from the airport to your office or from one location to other, you get something like travel in this highway for 10 kilometers and take a right and travel by highway 2 and go further up, something like that. You get a sequence, you get the route. Query plan is in some sense similar to that. It is the route that SQL Server needs to follow to run the query. So, what is this? To get started, what happens when you submit a query? First, the query is parsed, syntax is checked, binding takes place, whether the objects are actually present in SQL Server, the objects that you are referencing in SQL Server, are they present? It checks that. Next thing, it comes up with a logical tree. What is a logical tree? Logical tree is just a very basic sequence of operations that SQL Server needs to perform. For example, you have something called, let's say you have a query like select star from table, where column greater than some value, order by something. So what logical tree is? It is just a sequence of steps. Like first, I need to read the table. Next, I need to filter by this condition. And then subsequently, I need to sort the result because they have given an order by. I need to project the columns that have to be returned. So this is something like a logical tree. This is what comes up in the next step. Next, after that, it checks the most important step. It checks the statistics. What are statistics? Statistics are internal data structure which provides information how the values are distributed in the column. Let's say you have a table called 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 country, and there is a column called population. So what statistics tells is in that table how many rows equal to 10,000, how many rows between 50,000 to 1 million, and so on. All these kind of how the data is actually distributed, how many rows for a particular value, that is provided by statistics. So where statistics comes into picture over here is after coming up with the logical tree, what it has to do is it has to know how many rows will be returned by each operation. For example, if I'm going to filter, how many rows am I expected to get? The join, how many rows is it going to return? These kind of things, it actually refers the statistics and then it estimates the cost and comes up with the list of possible query plans. Among them, it finds the cheapest possible plan. So after going through this process, it comes up with the cheapest possible plan, and I hope you would have understood that the in this entire process of finding the cheapest plan, statistics play a very important role. Depending upon what inputs the statistic returns to the optimizer, the the cheapest plan is actually obtained. So So what's the issue with this kind of design is sometimes you can have incorrect plan choice for a particular query. This particular plan may not be very accurate. Why it happens? It can be because you may have inaccurate stats. As I said, statistics play a very important role in deciding which kind of operator, which kind of query plan I need to use, which kind of operator I need to use. Something like like index seek. Should I use an index seek or do I do a table scan? Do I use nested loop join or shall I use hash join while processing the joins? Which algorithm to use? What is the method I should use for sorting? All these are decided based on the statistics. So statistics may not be accurate all the time simply because by default it is not updated in real time. It is updated when at least 20% of the table changes. Prior to SQL Server 2016 and earlier, it used to be 20% changes on the table for the statistics to be updated. Now in 2017, you have something called dynamic threshold for coming up with the list of changes required for a statistic update. But still, on a million row table, at least you will need about 50,000 to 100,000 rows at least. Earlier days it used to be 200,000. At least 100,000 rows of change for a statistic update to be triggered. So more often than not, you don't have the completely updated stat. So because of that, you can have an incorrect plan and eventually have poor performance as well. Second thing is another very common thing is because of plan cache reuse. As I said, the query optimizer checks the stats, comes up with the cheapest plan, and then that particular plan is cached in the plan cache. So it is maintained in the plan cache. When the same query comes again, it doesn't go back to check the stat to come up with the plan because it takes too much of effort for SQL Server to come up with a query plan at each execution. So it goes and reuses the plan that it created last time, which is good. But sometimes the problem can be like, I hope some of you have used parameterized queries. What are or aware what is parameter? What are parameterized queries? Is when you let's say you have a stored procedure with a parameter variables. So for the first time when you execute, depending upon the value that you pass for the parameter, the query plan is created. In the subsequent time, you may pass a different value, but the same query plan that was created during first time gets reused. So the problem with this is, let's say my first time when I executed, the query plan was created for my first value that I passed to the parameter, and the second value that in my second execution, the value I pass, if it is drastically different in terms of the number of rows it's going to return, then the query plan may not be suitable, right? Because it is using the first execution's query plan, right? So, so this kind of problem, people call it parameter sniffing problem, especially to explain it a little bit more. For example, I have exe usp underscore something, and I have a variable as a parameter. First time when I pass your value, some value, that for that value, let's say the table, the stored procedure actually returns 90% of a table, or 900,000. If the table is 1 million, it returns like 900,000 rows. So first time when this execution goes, what happens? It will go and check the stats. It will see that it has to return 90% of the table. Instead of using an index, it would have felt it's better if it uses a table scan or a clustered index scan, right? Whereas in the subsequent time when it runs, let's say the parameter that was passed was going to pick only 10 rows. The second, third, fourth executions. So what would happen? All of these will get table scans because the query plan gets reused. So if because the first one picked majority of the table, you got a table scan, and the subsequent ones, all of them just get table scans as well, even though index C would have been the right operator. So this kind of problem is called parameter sniffing problem, or it's basically due to reuse of the plan stored in the cache. It's in some sense a chicken and egg problem of sorts. If you don't reuse, then SQL Server can be very slow. Obviously, for each execution, you cannot go and create query plans every time. If you reuse, there are chances that you may reuse an inappropriate query plan. As of date, till prior to SQL 2017, we are the only options that we had was to wait for SQL Server to fix it automatically, like we have to wait for restart or wait for an update start. When the statistics are updated, the new query plan for that particular object is created, and so it causes a recompile and the new query plan comes in. Or some people actually go and hard code some query hints, meaning you can specify they change the code to specify a particular operator or a particular index, so that always the query plan is forced as per the query hint used. In 2016, you had another feature called Query Store. So in Query Store, you can actually force the query plan as well. You can actually force the database to use a particular plan. All these approaches demand some kind of action from you, the database administrator, or the developer, or the people handling the application. So 2017, what it attempts to do, it attempts to solve this problem on its own. How it does the adaptive query processing and automatic tuning features as well. Both actually, it is a self-learning and a lot more intelligent query optimizer. It actually learns what it takes its input from in two ways. One, it, it it develops certain amount of intelligence, as I said, during the execution. It is able to make minor corrections if it realizes the plan is not going that well. Second, it is also able to take feedback from the previous execution and make adjustments. So in this particular session, I will be actually going through the scenarios where adaptive query processing is is, is how it is going to work, and 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 what are the scenarios it can actually help you improve the performance. In some sense, similar to the analogy I explained a little while ago, like the route. I explained that when your query plan is like a route plan of sorts, like the path that one needs to take, the recommended direction that Google Maps gives you for traveling from one location to another. Take highway 1, highway 2, go 100 kilometers on this highway, and so on. But this adaptive query processing, the change it brings about is it is just like this intelligence. Let's say you are traveling in a highway and you are following the Google Maps. You are traveling by highway 1. Suddenly you notice there is a traffic jam because of an accident or something. You don't end up waiting for hours. What typically you do, you look for other routes, right? Because this route is not working as expected. So you take other route and you try to reach the destination, next possible route. In some sense, adaptive query processing is similar to that. It starts the execution and it kind of understands, okay, this is not going as we expected, so let me make this particular change. Before I just continue, I just wanted to know if everybody is following, and am I too fast? Because the reason why I'm asking this is there's a webinar, so I don't see whether you guys are following what I'm talking, and whether. So can you just on the chat window if uh, if it's if it's fairly clear, and if you guys are with me, can you just ping a little message? Hello. No. Okay, fine. Keep the questions flowing. If you have any questions, you can shoot it, or if you have any comments or something, you can always write to the chat window. From time to time, I will take a look at it, or Manohar can actually inform me. Okay, let's move on. Adaptive query processing actually helps in three scenarios. One is memory grant feedback, adaptive joins, and interleaved execution. So let me explain these scenarios one by one. It doesn't mean that, okay, with SQL Server 2017, every query will get intelligent plans. Every query is very smartly just going to get automatically tuned. No, there are certain scenarios where this adaptive query processing can actually help, or it is applicable. We will see these three scenarios, and I will also brief about automatic tuning capabilities of SQL Server 2017 in this session. Adaptive joins. Adaptive joins. First, before I get into that, let me actually quickly uh, brief you about what kind of join types are there in SQL Server. Most of you, I hope, would have used joins, right? Right. So select star from table, table A, inner join, table B, on, table A dot column 1, table A dot ID equal to table B dot ID, something like that. So when you have these kind of joins, SQL Server has three join algorithms or three join operators in execution plan to choose from. One is nested loop join, other is hash match join, other is third one is merge join. Each of them are picked at certain scenarios. When both the tables are small, when both the outer table and the inner table, the two tables that are participating in the join, if both are small, then typically you get a nested loop join. And or if one of the table is big but indexed and one of other table is small, you get a nested loop join as well. Hash merge join, typically when both the tables are fairly big in the sense of 50,000 or 100,000 rows, and they don't have an index, then it uses hash match join or hashing algorithm to process the join. Merge join is used when both the tables are big and they are indexed. You have an index on the joining column. When I mean index, I mean table A.id and table B.id both have a join, both have an index on it. So these operators are picked typically by the number of rows that are present in the table or the number of rows participating in the join. So typically, so you know that if the stats aren't well properly updated, then you can obviously have an incorrect plan choice as well. Enough of slides and talking. Let me actually get started with the demo. Is the screen visible? Uh, okay, okay, good. Okay, right. So let me explain. I have this query, very simple query, joining order table and stock item table based on a particular value. Let me run this. Just give me a moment. I just need to drag this thing. Okay, the pop-up was actually disturbing, so it's actually trying to position it somewhere else. Yeah. Okay. Let me show the execution plan for this. I am just enabling the execution plan. This is SQL Server 2017. I have a database called Worldwide Importers, which is a sample, one of the sample database available. I'm just going to run this query. What I get over here, let me zoom it. I know that the query plan here. This one. Okay. If you notice here, yes, you have a new operator called adaptive join. What it actually does, let me explain that. Let me zoom. Are you all able to see when I zoom? Do you all see when I zoom? If I zoom, do you see the magnified image? I just wanted to ensure. Okay, great, nice. Okay, so observe this column called or adaptive threshold rows. It comes like the sixth or the seventh row in the query plans properties, adaptive joins properties. It says 68 rows. So what it means is when it comes to adaptive joins, Means what it does is it comes up with something called adaptive threshold rows, and says if the number of rows coming from the outer table is greater than adaptive threshold rows, then go for a hash match join. If it is less than the adaptive threshold, then go for nested loop join. It has this intelligence, something like this. If you're traveling on highway 1 and if you're stuck on that highway for more than 10 minutes, take a diversion. If not, proceed with the highway. It has that particular intelligence to make that minor adjustment to ensure you get optimal performance. So in this particular case, observe the estimated number of rows at the bottom of the screen. The estimated number of rows, it says, is estimated number of rows is 206 rows, and how many rows did it actually get? Actual number of rows is also 206, which is greater than the threshold row 68. Right? So it estimated a hash match join because its estimate is more than the threshold. And actual join type, you notice the third row, it tells us that yes, as expected, it was a hash match join that was used. So the secret sauce or the magic happens with the adaptive threshold rows, which helps it actually dynamically switch between nested and hash match joins. Let me show this in action, meaning let me create a scenario where it actually dynamically switches the query plan. For that, I need to delete some rows. So let me delete some rows so that the stats are not updated, and then let me show you how the query plan behaves in older optimizer, which is in SQL 2016, and how it behaves in SQL 2017. I'm deleting some rows. And now I'm switching the compatibility model. Let me turn on the query plan. Okay. And if you see over here, it has estimated number of rows is 95 rows at the bottom of the screen, and but in reality it got only 36 rows. Actual number of rows is 36, and it is a hash match join. Now let's see what happens with the new optimizer. Let's over here actually used adaptive join. Okay. Is adaptive equal to true, and it has fixed the adaptive threshold at 48 rows. Estimated number of rows, if you notice, it is 95.9, but it estimated 95 rows, adaptive threshold is 48, so it estimated at join type is hash match, but in reality, it got just 36 rows. Actual number of rows is 36. So actual join type, the third row, if you observe, it went to nested loop. Even though the estimated join type was hash match, because it has adaptive query processing, because it is less than the threshold of rows, it used nested loop join. Clear? So as I explained, it go check the threshold and decides whether to go for hash match or nested loop. Are all queries eligible? No. It can take the decision only between nested loop and the hash join operators. If merge join is participating, then it may not be able to decide. As of now, it is supported only for batch mode operations. Batch mode operations are one of the, there are two kinds of execution modes. One is row store mode, where each row is individually processed, whereas batch mode, it is able to process groups of rows or groups. So this, as of now, it is available only in batch mode. So as you would have realized, the secret sauce is with the adaptive threshold rows. How is it determined? It is determined by cost. When the query is submitted, it actually goes and checks for this particular query what could be the ideal adaptive threshold. If it goes more than this, when to switch to nested loop plan and when to switch to the hash join algorithm. It comes up with this number during compile time, but even though the plan is reused at each execution, the choice between nested loop and hash join alone differs. That decision is taken during runtime depending upon the threshold. So this way you actually strike a balance. You still reuse the plan, but you are just switching between two operators depending upon on the runtime factors. On the query plan, I explained these things already. Actual join type, adaptive threshold rows, what these are. Clear? Any questions so far? Okay. Let me proceed. Memory grant feedback. Next scenario that we are going to look at is something called memory grant feedback. Okay, there is a question from someone. Can we find what is the threshold? Yes, as I said, and as I just now demonstrated, give me a moment. As I just now showed you, over here on the query plan, you actually, at the compile time, you actually get the threshold is actually defined. It's the fifth or the sixth row over there. It says 48 rows. Okay. I'll take up further questions as at the end of the session as well. I hope my answer or address your question, Jyoti. Okay. So next thing that we are going to see is memory grant feedback. What is this memory grant feedback? Imagine this. You have a query. First time when it's compiled, and it actually checks the stats. It estimates that the query is going to probably return about 100 rows. But unfortunately, it returned like a million rows. What happens is, because it estimated only 100 rows, it gets certain amount of memory granted, or at compile time it says this particular query needs 10 MB of memory to be granted for it to run. So at compile time, how much of memory it needs is it's estimated. But during runtime, only 10 MB is granted, and it has to process, unfortunately, 100,000 rows. It doesn't have enough memory. What it does, it goes and writes to 10 dB and does its further processing. This can cause a performance problem. Something called MDB spill happens because it doesn't have enough memory granted for it to run. So it has to make use of the MDB. Other way around also possible. It estimates 100,000 rows, but what it actually got was just 100 rows. So it was granted 100 MB of memory, but it used up only 10 MB. In such a scenario, what happens is, if it's an excessive grant, obviously it's waste of memory. The memory remains unused when the query is actually running, and and it also means that so it has to the query has when it is running, it has to ask the memory manager to grant the amount of memory it needs. So it has to wait longer time because it is asking for longer, larger amount of memory, right? So both the things, if it is the grant is lesser or if the grant is more, it can cause performance problem. Reason is obviously again incorrect estimate on stats, or it can be a performance mapping problem, which I explained earlier. How adaptive joins actually address this is something we will see now. Okay, again, I'm going to switch the query planners, sorry, the compiled level to older version, and I'll run the query and to show what happens, how adaptive query processing actually addresses this particular problem. Sorry, I forgot to turn on the query plan. Just give me a minute. Maybe run this. If I hover over my mouse against the memory grant, observe the memory grant area. It says 68. This is in KB, so it says 68 MB that has been granted for this particular query. Let's take a slightly deeper look. Let's right click and say properties and say memory grant info. And let's so observe the max used memory. That is the amount of memory it actually used, the query actually used. The maximum memory it used was just 9.7 MB, even though it requested 68 MB, right? So, which is obviously a problem because it hasn't used most of what it was granted. Now, let's run the query against 2017 compatibility model. I'm going to run thrice to demonstrate something this way. Okay, I'm switching and I'm running it against 2017. Okay. So if you notice here, first one again, first execution, even on this, it has taken 68 MB. Second one, if you notice, on the second execution, if you notice, it has taken just 10 MB. And let's observe what is there in the properties window as well, how much it actually used. And if you observe the second one, what we see is it has just used 9.6 MB. It was granted 10 MB. So it has, why there is a change, if you are wondering, it is because of the memory grant feedback aspect of adaptive query processing. What it actually does is every time when it realizes like either there is excessive grant or it has been granted less, on the subsequent execution, it makes the adjustment for the amount of memory that needs to be granted. It is, if it realizes it has granted really high and the query did not use, after the execution is completed, it goes and feedbacks to the query optimizer saying that this particular plan you granted lots but it didn't use. Next time, make the adjustment. So next time when the same query is executed or when the same plan is accessed, it makes the adjustment to the amount of memory given. If it is higher, it will reduce the amount granted. If it is lower, it actually increases the amount of memory that has been granted. So, as explained, sometimes, so if it is an overestimate, if it has been granted uh, two times more than what it actually needs, then it is categorized as an overestimate and it makes an adjustment. Underestimate is the case when the memory actually spills over to when it uses 10 dB, it automatically, or if when there is a memory spill, it understands it's an underestimate and it makes the adjustment. One of the key things out here is it does not actually uh, it it does it is a completely asynchronous process. It does not after the execution is completed, it goes and just updates the plan cache or the query plans properties. So it doesn't hurt your execution. It doesn't do anything when your query is running. It is done after the query has actually completed. Okay, next thing I have is interleaved execution. To explain that, let me open up this. So what interleaved executions are when you run multi-statement table value functions. I'm not too sure how many of you have used it. There are two kinds of table value functions. One is a scalar function, which is capable of returning just a single value, and then you have table valued functions, which are capable of returning a result set, a group of values. You have these two kind of functions, and then you also have multi-statement table value functions where within the function you can write multiple lines of statements and you can return a table. When you use these kind of functions, prior to in the older versions of SQL Server, it used to come up with a blind estimate, meaning in what it used to do is, let me open up the query itself. The older versions of SQL Server, it used to do a blind estimate of the number of rows returned by the function. It passes. So in SQL 2016, it used to estimate 100 rows as a fixed number of rows that is returned by the function. In 2014 and earlier, the number of rows returned is just one row. From 2017, what it does is when it has a table value function and the value that is passed to it is a scalar value. It is either a variable or a hard coded value. Then at compile time, it actually executes that particular function. It actually executes, finds out the number of rows that are being returned, and uses that to design the query plan for rest of the query. In other words, it runs this function at compile time and then identifies number of rows that are returned, and then it passes that to the remaining portion of the query. Let's again quickly, I think we have just few more minutes, so let me just quickly run this particular query in older version first. You notice here the number of rows is 100 and the actual number of rows is 136. So no matter what value I pass, it just comes up with the estimate of 100 rows. That was in SQL 2016. SQL 2017, it actually runs this and comes up with the estimate. Over here, if you see, it is a lot more. It is obviously accurate perfectly because it has actually run and it has come up with the estimate. So explain these. As I said earlier, it used to go with a blind estimate. Now it actually runs and comes up with the estimate. This particular interleaved execution applies only when in the queries, only when you pass a scalar value. If you pass the columns value, it obviously cannot estimate it at compile time. So it will still follow the blind estimates as per the previous model. When you use the scalar value, it actually comes up with the accurate. Okay, with this, I'm done with the adaptive query processing section. I have the final section called automatic tuning, which I will very, very quickly go through with you all. So, how many of you have heard of, okay, I'm always in the physical presentation mode where I continuously ask questions. Now I realized, okay, I'm on a webinar. It makes it harder to interact. So let me not ask the question, let me explain it myself. So what is automatic plan correction? Regression. What is the regression problem? Some of you would have faced this problem. A query runs at certain performance. You make some changes to your application or you introduce new indexes. Suddenly the performance starts dipping very badly. So this, after a particular change or after a particular event, actually, the queries start performing very, very badly. The same queries start performing badly. So we want to fundamentally figure out which queries are performing badly and we want to correct them. Earlier version, SQL 2014 and earlier, the only option you had was to use extended events trace or profiler to identify regressed queries. 2016 came up with query store to identify regressed queries. It can automatically, it can just tell you, a simple report will tell you these queries actually had faced regression. They were running fine, but now they are not running fine. And you need to take some kind of action, either force the plan using query store to ensure optimal performance. Whereas 2017, it attempts to fix this problem automatically. What it does is it actually detects if the plans have actually regressed. If they have regressed, then it actually forces the last good plan, last known good plan. For example, notice here, I have plan 1 and I have a single query. It has had 4 different plans, plan 1, plan 2, plan 3. All these had typically usual kind of execution time, but suddenly plan 4 is giving incredibly high execution times or consuming incredibly high resources. What SQL does is when it detects this, SQL Server 2017 is capable automatically switches the plan to plan 3, last good known plan. So this actually has absolutely no code change at all. You don't do anything. SQL Server does it automatically. All you need to do is turn this setting on in SQL 2017, alter database name, automatic tuning, force last good plan equal to on. Let me very, very quickly go ahead and for this automatic plan auto tuning tool, we have to enable query store. Let me enable. I have enabled query store. Now, what I'm going to do is I'm going to run this particular query. I'm passing a value 2 to this particular query. It will come up with a query plan. Then I'll flush the cache, I'll pass a different value. It will come up with another query plan. So I have 2 plans for the same query. And then subsequently, I will show, so when an inappropriate plan is actually picked, how it actually manages to post I forgot to, okay. Over here, important thing, just note for 2, it has picked hash match because it is returning about, it is reading about 1.9 million rows. Okay. I just need to populate this a few times so that the, yeah. Let me open up another one. Okay. So now I'm going to clear the cache and run it against a different value so that I get a completely different plan. Over here, I'm getting stream aggregate because the number of rows I'm reading is significantly lesser. So for the same query, right now I have 2 plans. So what I'm going to do is, so when the big values are bigger, typically you need to have hash match. When the values are smaller or number of rows that are big process is smaller, then typically you have a stream aggregate. Now in the cache, right now, I have a stream aggregate. Now I'm going to pass, run it against type 2, type equal to 2. If ideally it should have a hash match, but because the last execution gave stream aggregate, it is going to come up with stream aggregate. Cache. Okay, let me just run this now. Okay, I think I'm probably doing this little slowly. So in some sense, it is automatically tuning it to switch my operation. Okay, so this particular feature, as I said, is capable of switching if it notices poor performance. Let's right observe what it has actually done from this particular DMDB tuning recommendation. Excuse me. Okay, over here, if you notice, the previous plan was stream aggregate, and then if I run it, and then it continuously goes with stream aggregate, which is actually giving it a bad performance. And suddenly, at the execution number 13, it manages to switch to hash match because it realizes that this particular plan is not suitable for fetching large number of rows. If you go and check over here, the DMDB tuning recommendations, it actually gives me the reason as well why it actually forced a particular plan automatically without me doing anything. It says, okay, let me zoom this for you. The average CPU time changed from 40 milliseconds to 498 milliseconds. So CPU time had a drastic change, so it actually went ahead and forced the plan automatically. So this particular feature can potentially stop many of those unwanted odd time calls the DBAs receive saying that the performance is awful. Why we don't know. Suddenly the queries are performing slow. Those kind of problems due to plan cache reuse or statistics can be avoided if by turning this particular feature on. So last one. This automatic index tuning. This is available only in Azure or Azure SQL database. What happens in this is when you create Azure SQL database and when you run queries against it, if you turn on automatic index tuning, it can study your workload and automatically create indexes or remove unwanted indexes. One of the best things is it automatically identifies a quiet period, meaning it rolls out the new indexes when 80% of the database is actually free or it is the utilization is less than 80% for the last 20 minutes. And it also, when it is creating, it uses online on to ensure that this operation can be rolled out when the database is available. It does not have any major blocking impact. Not just that, it follows this three process of learn, adapt, and verify. Learning is when the queries are actually run against the Azure SQL database. It studies it and it identifies what are the ideal indexes. It learns it. Adapt is it actually rolls out those indexes. Finally, verify happens verify it happens after the rollout has been done. After the rollout has been done, it actually checks if the particular index is giving the optimal performance or not, whether it gives us the right expected performance. If it doesn't give, it actually rolls back the change as well. Let me it won't be a live demo for this one because it takes one day to study the workload and then it comes up with the recommendations. So I have created this database called what I did was I created a blank database called automatic index tuning. On that, I ran some workload for a few hours, let it run for a day, and then subsequently, I turned on automatic query tuning. If you notice, I have turned it on for this one. So if you see, force plan is the automatic plan correction which I explained. Create index and drop index available only in Azure. So it is. I have turned all these three options on. After I run the workload for a day, what I got was these. Actually went ahead and created these indexes automatically. It identified it and created these indexes. One thing is, it is unlike our old missing index DMV or the database tuning advisor. Unlike them, it doesn't recommend like 100 indexes or for all the possible queries. It doesn't try to come up with the recommendation. It uses lot more complex algorithm. It uses artificial intelligence and machine learning concepts to actually realize which index would be suitable, and the recommendations that are provided are lot more deeper and accurate as well. So with this, I'm done with the session. So I have added the references as well. You can check out these for more information. I'll be sharing the slides with Manu. Probably he will be able to distribute them to you as well. With this, I'm done. Manohari can take over the control. I'm happy to answer any questions.
Thanks, Nagaraj. That was a wonderful session, and hope you're able to see my screen.
I can see your screen.
All right. I'm just not seeing the border green line, but yes. So if you have any questions, please start typing in the chat window, as well as you can go ahead and post your questions on the Facebook group, where we'll answer the questions for you. A quick word from our sponsors. The SQLMaestros, which is again a part of eDominant Solutions, has some learning solutions. SQLMaestros conducts advanced trainings on SQL Server and whole MS Data Platform stack. They have SQL Masterclass and other online trainings. There are also hands-on labs, which is a very wonderful resources available online. You just need to register. Few of them are free, but most of them are paid. There is annual subscriptions and corporate subscriptions as well. So hands-on labs is a very good place to go and actually do things and learn. There are on-site trainings and SQL Server health checks that are connected by SQLMaestros. So all the information is available on SQLMaestros.com. The hands-on labs is this is just a sample screen where it's displaying like few of the labs. There are about 200 labs on the site, so it's a very, very useful resources that it's a must-have in your toolkit. With that, thank you for your time and thanks for attending the webinar. Thank you, Nagaraj, for giving a wonderful session. Please post your questions and we will be uploading this slide deck soon and along with the script resources from Nagaraj. Thank you, everyone. Have a great day.
Thanks a lot. Thank you.